Hello, Mr. Allman here, and this is your Allman Cast on water chemistry. Now, in your academic past, you went through a chemistry class in which you learned all about the matter that makes up the natural world. All the matter in the universe is made up of one of a handful of elements. When we look at what's here on Earth, and more importantly here in biology class, what it is that makes up living cells, we see that it's actually a very, very small number of things. You should remember the atomic theory, which states that atoms are composed of subatomic particles, the uncharged neutrons and the positively charged protons, which are packed into a very dense nucleus in the center of the atom, and then the very, very small negatively charged electrons, which occupy a space outside the nucleus known as electron orbitals. In biology, most things are made up of carbon, hydrogen, oxygen, and nitrogen, as well as several dozen minor and trace elements, which we need very small amounts of in order to ensure our relative health. This is as true for humans as it is for plants and bacteria. The condensed periodic table that you see at the bottom gives you a rudimentary view of the organization of the electrons in the orbitals. Now, the nerds amongst you can use quantum mechanics to be able to explain the exact organization of those electrons. But to biologists, the only thing we care about is the fact that all of the biologically significant atoms that we find in living things are unstable. And because they are unstable, they bond. Bonding is a way to enable stability between atoms based on their electron configuration. There are two significant types of bonds that hold atoms together. There are the boring ionic bonds, which transfer electrons from electron donors to electron acceptors, stabilizing both parties. Most ionically bonded compounds that we come in contact with are soluble in water. Therefore, we don't care a lot about ionic compounds because these salts, once they get inside of us, are dissolved into individual ions that no longer have those bonds with each other. Covalent bonds, on the other hand, are prevalent. These are hugely important to ensuring that all of the important molecules of life maintain their structures. Covalent bonds are the sharing of electrons, and particularly because of the electron bonding configuration of carbon and to some extent nitrogen, there are nearly infinite combinations of covalently bonded molecules that can exist. That's what allows for the 90 to 100,000 different types of proteins that we find in us because of those different bonding combinations. Now, not all bonds are created equal. For this reason, we have polar molecules. Polar molecules, the most important of which is water, are those molecules where the electrons are shared unequally with each other. There is a covalent bond between the central oxygen and each of the two hydrogens in H2O. Now, oxygen, which is highly electronegative, is greedy for electrons. Those electrons, which are supposed to be shared between oxygen and hydrogen in a covalent bond, end up spending most of their time in the orbitals surrounding the oxygen atom, and not spending very much time in the orbitals surrounding the hydrogen atoms. That leads to an unequal distribution of charge in the molecule. So, the oxygen has a delta negative, showing that it has a slightly negative charge, whereas the hydrogens each are delta plus, showing that they have a partial positive charge. This charge is not as much as what you would see in an ion, like a sodium or a potassium ion, but it is enough charge to make it chemically significant. What that leads to are hydrogen bonds. Hydrogen bonds are the attraction between highly polar molecules. You can see here a molecule of ammonia, NH3, and water, H2O. The hydrogen is delta plus, it has a partial positive charge, whereas the nitrogen in ammonia has a delta minus, it has a partially negative charge. Positive is attracted towards negative, leading to the formation of a hydrogen bond. Hydrogen bonds end up influencing in great ways the behavior of molecules, but they are in no way permanent. They are much weaker than ionic bonds and far, far, far weaker than covalent bonds, and so it only takes a little bit of energy to be able to break those apart. That's why proteins will denature under high temperatures, because most of the three-dimensional shape of a protein is held together by hydrogen bonding. So a little bit of heat unravels those proteins as it breaks all those hydrogen bonds. Now what you should consider as you look at the chemistry of water is, why is it that you and all other living things are mostly made of water? How is it that the structure of water determines all of its amazing properties? And most importantly, how are those unique properties of water utilized by living things? Particularly by humans, but also by plants and by bacteria and all living cells. Water is so important to living things that much of our exploration of space focuses on looking for that very molecule. And the discovery of water on Mars, the discovery of water on exoplanets outside our solar system, is linked to our belief as to whether or not those places can maintain life. Life as we know it could not exist without water, so as we look for life on other planets, water is exactly the compound that we're going to look for. So water is needed for life because living things are made up of more than half, and in our case, 60 to 70+% of our body is made up of water. Now, as you've learned in previous units, there's a lot of chemistry going on in interactions between molecules. Now, the chemistry of life is a solution-based chemistry because all of that empty space in our cells and the empty space surrounding our tissues is made up of water. Now, Earth, as far as we know it, and certainly within our solar system, is unique in its amount of liquid water. And solutions require liquid water in order to be able to dissolve their solutes. Water is one of the few substances that exists in all three phases at terrestrial conditions. We find water vapor present in the atmosphere in anywhere from 1 to 5%. We find liquid water present in all of the oceans, rivers, lakes, ponds, puddles around the world. And we find ice permanently existing at our polar ice caps and on the tops of mountains and trapped in glaciers. Here you can see the distribution of water across the Earth. 97+% of it is saline, meaning has high amounts of dissolved solutes, particularly sodium, magnesium, and carbonates. Only 3% of that is fresh water, of which the vast majority is locked up in ice on our polar ice caps and glaciers. 30% of that is in the ground, and far less than 1% of that is present in lakes, rivers, and swamplands. So our presence on the shores of Lake Michigan is really an aberration as we compare the amount of water that's available to life around the world in comparison to what we have here in Chicago. Water has many unique properties, and those properties are super important in terms of maintaining life. A lot of living things take advantage of water's properties in order to be able to accomplish life functions, growth, development, reproduction, etc. So without water, we wouldn't be here. In class, you'll be exploring some of these properties, as well as some specific examples of how living things utilize those properties to survive. Thank you for watching, and let me know if you have any questions.